topic that tends to confuse people. Something called linear independence. Linear independence. Okay, so the idea is that we are, in some sense, our current goal is to create a coordinate system. Okay, so you have a vector space. It's an abstract vector space, right? You don't have a coordinate system on it. Just like in Euclidean space, you have a coordinate system, right? Everything in every point in space can be assigned, some set of coordinates. But what about for abstract vector spaces? How do you do that, right? Can you do that? So our goal is to create a coordinate system for an abstract vector space. Okay. And what we're going to see is that we'll need some notion of minimality. Okay, it will become evident. That something like a minimal spanning set will be needed. Some sort of minimal spanning set will be needed. Okay, so if you think about, let's say, if you think about R2, right? What you have is that your vector 1, 0, and you have your vector 0, 1, right? Vector 1, 0, and 0, 1, and everybody in the space can be expressed as some combination of those guys, right? Usually call this guy I and this guy J. Right? Everybody can be expressed as some combination, right? If I have some point, 3, 5, that's going to be 3I plus 5J, right? Everybody can be reached as by these guys, and there's sort of a minimality about it. If I throw out any of these guys, then I don't have enough. Right? I don't have enough. There's no redundancy involved. Whereas if I considered the set I, J, and negative I, so suppose I said, oh, I'm gonna take these guys as my spanning set. Well, certainly they span, right? These guys span, and if I throw in one more guy, then it's still gonna span. But I sort of have too many vectors, right? I have more than I need, right? I could say, oh, this guy, 0, 3, is going to be 3 of J, and 1 of I, and 1 of negative I, right? So there's sort of that redundancy results in sort of multiple ways of getting to the same object. Right, so I could express this as 3J. I could also express this as 3J plus I plus negative I. Right, there's sort of like there's a redundancy involved. Okay, so right, so yeah, so this would so that is, I could express this thing as 3 of J. But anyway, so okay, so I'm sorry. Let me go. Okay. So the crucial definition or concept is the following. Turns out to be this: something called linear independence. Linear independence. And here's the definition, and it will seem a little bit peculiar. So you have V, a vector space, and you have some vectors, V1 through Vn, in this vector space. Okay? So we say that the set of vectors v1 through vn is linearly independent if whenever some combination C1v1 plus C2v2 plus Cnvn yields a zero vector, we know that all the Ci's must be zero. Okay. And otherwise, we call the set linearly dependent. We call the vectors linearly dependent. Okay. So linearly dependent means you're not linearly independent. Okay. So another way of just rephrasing this thing, what this is saying is that the only way you can get the zero vector, the only way you can get to the zero vector as a linear combination of these guys is to take zero of each one of them. Okay. There's only one way to get to the zero vector, and that is the trivial way. You multiply everybody by zero and add them together. Okay. So the only way to express zero as a linear combination of the VI is the trivial way. The trivial or the obvious way. Right? Given any bunch of vectors, you can always get to the zero vector as a linear combination. Just multiply everybody by zero, add them all together, you get the zero vector. Okay. And this is saying that if there's no other way to get to the zero vector, then we call these guys linearly independent. So this is the definition that seems sort of peculiar, but in fact. This is the definition that that will allow us, will enable us to have a coordinate system. It'll turn out that this is exactly the condition that one needs to create a coordinate system on some set. Okay, so let me just give some examples to make this concrete as usual, right? So the simplest example is say 1, 0, 0, 1, right? In R2, right? In R2, this is an example of a linearly independent set, right? These guys are linearly independent, right? If you have some, right? This set is linearly independent, right? For if some combination is the zero vector, right? If you have some combination of these guys that yields a zero vector, well, you know then, right? A, B, A is 0 and B is 0. Right? Just by calculation, you see that the only way you can get the zero vector is by taking 0 times the first guy and 0 times the second guy. Okay. So that's linearly independent, and we see that this set here. I'm going too fast. Let me stop. we see that this set here is linearly dependent, right? Because there's an obvious non-trivial way to get to the 0 vector, right? We take this guy and add it onto this guy, right? 0 of this guy plus 1 of this guy plus 1 of this guy gives the 0 vector, right? So that was a linearly dependent set. Another example, more abstract. If we're looking at the polynomials of degree less than n, and we look at these polynomials, okay? So here's a bunch of vectors in our space, right? The function that takes 1 everywhere, p of x equals x, p1x. So we could, if we like, you can call this guy p0, p1, p2, pn minus 1. Right. These are all polynomial. Each of these guys is a polynomial of degree less than n. Each of these guys is a member of piece of n, right? And are they linearly independent? Are they linearly independent? Is there a non-trivial way of combining these functions to get the 0 polynomial? Right. Think about it for a second, right? Are these guys linearly independent? The question is, right, if C naught plus C1x plus C2 x squared plus Cn minus 1 x to the n minus 1 is the 0 function, right? If this thing is the 0 element, does that imply, and does that force all the Ci to be 0? Does it? Are you guaranteed that all the CIs is, if this thing is right, right, if this thing is 0 for all x, right? If this thing is 0 for all x, if this thing is the 0 function, does that mean that all the coefficients must be 0? Yes? No? Yes. Why? Can somebody explain to me why all the coefficients must be 0? Yeah, no.
Because all the powers will grow at different rates. Sorry, all the elements of the polynomials would grow at different rates. So x would grow at x would grow at a different rate compared to x to the power of n minus 1.
Yeah, so you're sort of saying there's no way we could make the other guys cancel off one of. There's no way that if you look at, say, the constant guy, there's no way we can combine the other guys to get negative C naught. That's sort of what you're saying. There's no way we can combine the guys of order n minus 2 and lower to get the guy of n minus 1, right? You're saying that the behavior of each guys is so different that you can't combine polynomials of different degrees to get a polynomial of a higher degree, say, of lower degrees to get a polynomial of a higher degree, right? So that's sort of like the intuition. Can somebody give a more watertight argument about this? For example, why must C not be 0? Amina.
Because at x equals 0, C naught would have to be 0 for that function to be equal to 0.
Okay, so you could say, well, look, this function is 0 for all x, so let's evaluate it at x equals 0. That gives us information. C naught must be 0, right? So then let's evaluate at x equals 0. C naught is 0, right? Itzong, you look unhappy. What's bothering you?
If x equals to 0, if c naught is not equal to 0 but it's still 0, right?
No, if c naught is not equal to 0, right? Suppose c naught is 1.
I see. Yeah.
We evaluate this thing at 0. We get 1 equals 0. No. Okay. Yeah. Okay. What about the other ones? What about C1, C2? Probably you get the joke by this point, Elena.
If you know that the one, like proof by induction, if you know that the one that has one fewer, like if we have from x to the power of 0 to x to the power of n minus 2, if you know all of those are 0, then you know the next one has to be 0 for all x. Like if you know that C naught, C1, C2, all the way through Cn minus 2 are 0, then you know that Cn minus 1 has to also be 0, so that for all x, Cn minus 1, x to the power of n minus 1 is 0.
By induction, huh? So you're saying that it's, let me think. So you're saying that if you're inducting on n, right? You're saying, well, if it's for P1, then it's obvious. And then assume that it's true for some arbitrary P, that if that for an arbitrary P, these guys are linearly independent. And does that imply that, so you're saying this, right? Suppose you know that x1 to xn minus 2, x minus 1 are linearly independent. Right? That's your inductive hypothesis, right? You're saying then that implies that x1 to xn are also linearly independent. Right? Is that true? Right? Because you'd say, well, look, C naught of the first guy plus C1 x plus Cn x to the n equals 0. I don't see how you can make that step, actually. Yeah, I don't see how you can make, right? Because you would know that these guys are linearly independent, but you don't know. I don't think it's possible to make that step, actually.
Well, if you know that all of the other C terms are 0.
You don't, right? All you know is that if we didn't have this guy in there, then they would all be 0.
Okay.
Right? So yeah, you don't know that. Yeah, Mia.
Could you do the same argument that you do for C naught for C1 if you pull an x out and then do x times C1 plus C2 x plus C3 x squared, and then set that equal to 0?
So you'd set that equal to 0, and then you'd
plug
say,
it and then evaluate at x equals 0, and then you would get that C1 equals 0.
No, you wouldn't, right? Because x is 0, right?
Okay.
Right.
Yeah,
So
I
no,
see.
but it's a good try. Anyone have an idea, Teresa?
Or I guess just a question. So
Yeah.
when you're explaining if you evaluated x equals 0, C naught has to be 0.
Mm-hmm.
Can C naught, or can the C's not be negative?
C's are any number, any fixed number. So
Okay.
you have any constants here, and they yield the zero vector, and you're hoping to show that in fact those constants must have been all zeros.
Okay.
Okay. So let's not take too much time on this. One way of showing it is to take the derivative, say, right? Take the derivative, and right, since this is the 0 function, its derivative is also the 0 function, right? And then when you take the derivative, well, this constant vanishes and this thing becomes a constant, right? And then evaluate it at 0, right? Evaluating the derivative at 0 shows that C1 must be 0. Evaluating the second derivative at 0 shows that C2 must be 0, and so on and so forth. Right? It's Taylor polynomials, right? Okay. So taking derivatives and evaluating at 0 shows that all the Ci are equal to 0. because you know that the right, you know that Ci is going to be the ith derivative evaluated at 0 over I factorial. Right? But that's 0. Right? By Taylor, using Taylor polynomials. Using your knowledge of Taylor polynomials. Okay. In any case, don't maybe you've gotten what you know about Taylor polynomials. Let's just think with our bare hands, right? You take the derivative and you evaluate it, right? When you take the derivative, you get C1 plus something else that vanishes when you evaluate it at 0. So that tells you that C1 must be 0, and so on and so forth. Is that clear or not clear? I feel like it's not clear. So I'm going to, so let's call this thing P, right? P of x, right? P of x equals 0, right? P prime of x is also equal to 0, right? P prime of x, however, is C1 plus 2C2x plus n minus 1, C n minus 1, x to the n minus 2, right? Evaluate P prime at 0 is 0, but P prime at 0 is C1, right? So C1 is equal to 0, and then you take the second derivative to show that C2 is 0, and so on and so forth. Okay. So those guys actually. These guys are linearly independent. These guys are linearly independent functions, vectors. Okay. So yeah. Okay. So number 3. In the same space, 1 plus x squared actually turns out, well, yeah, you just look at it, right? Is it linearly independent? No, right? It is dependent. Right. Because you can take, one of the first guy, minus 1 of the second guy, plus 1 of the third guy, plus 0 of the fourth guy, and you get the 0 function. There's a linear combination of these guys that yields the 0 function. Okay, so not dependent. The 0 element. Right? The 0 polynomial. Okay. So just to say it again, dependence is some sort of redundancy. Independence is, of course, the opposite of that. Independence is some sort of minimality. Okay. Let's make a simple observation about dependence and, of course, about independence. If you have a bunch of vectors and they are linearly dependent, that is equivalent to saying that one of the VI is a linear combination of the others. Okay. Right. So this is a more concrete expression of this statement that dependence is some sort of redundancy. Right. Dependence means that one of the guys, at least one of the guys, is a linear combination of the other guys. Right? That guy is redundant. to state this more mathematically, one of the VI is in the span of the others. Right? One of the VIs is going to be in the span of all the other guys. Okay. So let's just think about this, right? This is actually pretty straightforward. So I'll have you work through it. They're linearly dependent. Suppose they're linearly dependent. Okay. What does that mean? Being linearly dependent means just the definition. What is? Maybe you've forgotten it already. Linearly dependent means that, well, you can reach the zero vector in a non-trivial way. Okay. So we're going to try to go forwards. So assume the VI are linearly dependent. In other words, there exist coefficients Ci in R from I equals 1 to n, not all 0, such that C1 V1 plus C2 V2 plus Cn Vn is a 0 vector. Right? That's what dependence means, right? There's a non-trivial way of getting to the zero vector, right? There's a bunch of coefficients. They're not all 0, such that if you combine the VIs, then you get the zero vector. Okay. So why does that tell you that one of them must be a linear combination of the other guys? Does that tell you that one of these guys is in the span of the other guys? Let's say that C1 is non-zero. Let's say that C1 is non-zero. And I'm going to do something very, very unimpressive. I'm going to move it to the other side, and I'm going to divide by C1. Okay. Lo and behold, I realized V1 as a combination of the other guys. Right? Right. So I'm going to use a common mathematical abbreviation without loss of generality. Without loss of generality, assume that C1 is non-zero. Okay. Right. So that is, we're not making the argument any weaker by saying, let's suppose that the one that is non-zero is the first one. If it's not the first one, we just reorder it and make it the first one. Right? We're not weakening the argument. Right? We know that one of them is non-zero. At least one of them is non-zero. Let's say it's the first one. Then V1 is equal to negative C2 over C1 V2 minus C3 over C1 V3 minus Cn over C1 Vn. The end. Right. So, like, in other words, what we see is that V1 is a linear combination of the other guys. Okay. Right. So the forward direction is proven. Right. If it's linearly independent, then at least one of the VIs is in the span of the others. Okay, you guys see this? It's not at all an exciting proof, but this is a proof. Okay, and it's an example of how to write a proof. Right. Start off with what you're assuming. We translate it into something else, right? Assume that these guys are linearly dependent. Well, that means this. Okay. And then with that, if we have that, well, then one of the guys will be in the span of the other guys, the end. Okay. And maybe the most important thing for you here is this thing without loss of generality, right? You know it's going to be one of them. Well, let's just assume that it's the first one for convenience and without weakening the argument. You can't just assume whatever you feel like, right? I can't say, let's assume these guys are linearly independent. Without loss of generality, let's assume the conclusion, the end. Right? That's not legitimate use of without loss of generality. But as long as you don't weaken it, then you're okay. 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 And what about going backwards? What about going backwards? Suppose that one of the VI is a linear combination of the other guys. Well, how do you show that they're linearly dependent? Write it down. It's at this point you should be like, why are we even doing it? Okay. Take 30 seconds, take 10 seconds, maybe 15 seconds, however long it takes you to write it down, and write it down. Suppose that one of the VI is a linear combination of the others. Conclude that this collection is suppose that the first guy is a linear combination of the others. Conclude that the set is linearly dependent. It should take you. You should be done already. Okay, turn to somebody else and say, this is what I wrote down, or here's what happens. And then I'm going to ask somebody to come up and write it on the board, and we'll criticize that person. Okay. So you can you learn a little bit about writing.
V will use a linear combination of the other.
Okay, so it's going to just be assume equals.
And then you go back with the
Okay, who is bold? Who would like to come up and write down the argument? Where's my random number generator? I don't have it. I have a gigantic 20-sided die. I usually like in my back, but not today. Okay, somebody come up and write it, or I'm going to choose somebody. Elena, go ahead.
Okay.
You got it.
Yeah.
It's like just.
Yeah, so I'm pretty sure all of you have the idea. This is mainly just like how to write it clearly.
Yeah.
To make this equal to 0, would you just make C1 equal -1? And
So remember where we're starting, right? We're starting from one of the VI is a linear combination of the others, right?
maybe I shouldn't have come up here then.
Okay, go sit down. No. You can maybe you guys tell me what to write, okay? And I'll criticize my own writing. How's that? Yes, Haley.
V1 equals -C2 over C1 V2, like, and that, then you can plug that into V1 in the equation, and then the C1s cancel, and then it's negative V plus, like, negative that plus positive equals 0.
Okay, so let's start from the beginning. You say, well, assume, right, one of the VI is in the span of the rest of V1 to the end. So we write like this: vi minus 1, vi plus 1. Okay. Assume that one of the vi is in the span of the other guys. Okay. So in other words, i.e., vi is some combination c1 v1 plus ci minus 1 vi minus 1 plus ci plus 1 vi plus 1 plus cn vn. Okay. Okay, so why does that imply that these guys are linearly independent? Dependent. Excuse me. So how do you say? Right, we want to say thus blah blah blah. Thus the vi are dependent. Go ahead, Haley. You basically got it, right? You say vi is can be expressed as these guys, and then what do you do?
Plug it in. Well, I was plugging that one into the actual.
Yeah, that's a little bit more complicated than you need to, right? Because you in that case you're expressing all of your coefficients as quotients from the beginning, which is a little bit odd, but it's not quite necessary, I'd say. Right, you know that this guy is some linear combination of the other guys, right? What are we trying to get to? We're trying to say that, well, there's a non-trivial way to get to the zero vector, right? So what is it? How do we get the zero vector? Zane?
Right. I think I'm thinking about this completely incorrectly, but
Why
if
is-
you
why is he
express it,
talking?
express it like that,
Yes.
like negative c2 over c1,
Yes.
can't c1 not equal 0 for a solution to exist, and therefore it has to be dependent?
Say that one more time, I'm sorry.
If c1 equals 0 in
Mhm.
that equation,
But you can't have it, right? We
Exactly.
assume C1 is not 0.
I
right.
thought we assumed that the v1 is a linear combination of the others, and we're trying to
Are
prove dependence.
are you talking about this argument, or are you talking about this argument?
Well, this argument, but if we use that equation.
We're not going to use that equation.
Okay, what, but is it not correct to say that C1 cannot equal 0 using that equation?
Yeah, C1 wouldn't be 0, yeah.
And that is a linear combination of V1.
Okay. Looks like you guys you really want to use this expression.
But if all I'm saying is that if we use that expression,
Yes.
C1 cannot equal 0.
That's true.
Making it dependent.
That was what we assumed.
That's
at the
what we
beginning for that
assumed.
proof.
Alright, whatever. I don't understand.
Okay. So let's just come back here, right? We're trying to see that the VI are dependent. In other words, there's a non-trivial way to get this to the zero vector, right? We start off with the assumption that this guy is in the span. In other words, this guy. Actually, just for convenience, let me call it. Let's say that C. Let's suppose that I is 1. Okay, so without loss of generality, let's say that V1 is in the span of the other guys. C2 would be N. That way, you don't have to write I minus 1, I plus 1 all the time. Okay. In other words, V1 is some combination of the other guys. Okay. Then, can we express 0 in a non-trivial way? How do we get the zero vector? Does anyone see, there's sort of an obvious thing. How do we get the zero vector? How do we get an expression of the zero vector as a non-trivial linear combination of the VI's?
V1 plus C.
Thank you. Just say negative V1 plus C2 plus Cn is the zero vector, right? Ta-da, you found it, right? The non-trivial way of getting the zero vector, right? Because not all the coefficients are 0. This one is negative 1. Okay, right? This is a non-trivial way of expressing 0 as a linear combination of the VI. So they're dependent at the end. Okay. Mia, you look like you want to say something.
No,
No? You
I
okay?
don't.
Okay. As usual, my ability to read faces is a failure. Is weak. Okay. Wow, golly. Okay. 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 Let's see. Do we have time to do that? Maybe not. Okay. So let me just put up a theorem that we'll prove next time. So first let me make an observation about the observation. So the observation was that dependence meant that one was in the span of the others. Right? One guy was going to be at least one will be in the span of the others. And so independence is equivalent to what? None, right? Nobody is in the span of the remainders, right? No VI is in the span of the remainder. Okay? Just as a logical thing. That's logically equivalent to the statement. Okay. Okay. So now I'll state the theorem. Okay. Again, you have V1 to Vn in V a vector space, and what we'll see is this: V1 to Vn is linearly independent if and only if every vector in the span of the VI is uniquely expressible as a linear combination of the VI. Okay, so that is given any vector in the span, there's only one way of expressing it as a linear combination. Okay, there's only, just like, we already have the statement that linearly independent means that 0 can be expressed in only one way. Right? What we're saying now is something that seems a little bit stronger, but in fact it's equivalent. That, in fact, for each vector in the span, it can be expressed in only one way as a linear combination. So there's only one. Yeah, that's true for every vector in the span. And so the key part is, of course, this uniquely, right? Because without the uniquely, then this is a trivial statement, right? Of course, if you're in the span, you're expressible as a linear combination of the guys. Right? That's what it means to be in the span, right? So the key point is this word, right? Everybody in the span. For anybody in the span, there's only one way of expressing that guy as the linear combination of these things. Okay, and that's what we'll do next time.